Okay, recording is started. I will share my screen to show you the slides. Yes, you should be able to see now. Okay, this is the slide sequence we are going to use in this class today. We are going to talk about recursive methods, how to think recursively, how to understand that recursive methods run correctly, so how to verify them, and how to analyze them actually. Then we start talking about recursive data structures, and we are going to talk about linked lists as an example of recursive data structures. Then we are going to talk about some problems that use recursion to be solved. And that's it for this chapter, actually. Probably you all know recursion. In recursion, we use a simpler version of the problem to solve the larger version of the problem. And this kind of approach is very useful to solve many difficult problems. For example, in artificial intelligence, we use this method to search around all the moves in chess game, for example, or while proving mathematical theorems, etc. And you should have seen probably how to compute factorial using recursive algorithms and how to compute greatest common divisor probably. And we are going to talk about how to process linked lists, for example, recursively, and talk about binary search. You should all know about binary search and its recursive implementation problem, but we are going to go over it once more. Okay, recursion. Recursion is a problem-solving approach that in this approach we generate simple solutions to some kind of problems, not all of them. Actually, we can solve many problems by using recursions, or actually all of the problems by using recursion, but not always simple. But for some problems, some kind of problems, it is easier to think recursively and easier to simpler to solve recursively. In recursion, as you all know, we reduce the problem into simpler versions of itself. Actually, these simple versions could be only one simple version or more than one simple version. This Russian doll, Matrushka, is an example of recursion, actually. When you look at this doll and you open the first box, you see another Matrushka, the whole of it, actually. And when you open it again, you see another one. When you open it again, you see another one, and it goes and goes until some very small doll that cannot be opened up. So recursive processing on this doll can be considered like this. If there is one figure, if you cannot open that up, just solid one figure, then you can process it, do whatever you like on that figure. If it is not one figure, then you take out the other figure and do whatever you are to do with that figure, and you process the figures inside the matrix inside by a recursive call for the same method. Process the figures nested inside the outer figure in the same way, right? We recursively process it. So again, we try to figure out, we try to check whether it is one figure or not, and take out the other figure and process whatever inside it. And while whatever is processing whatever inside it, we call it again and start all over again. This is recursion. You all know what recursion is. For example, in searching an element in a sorted array, we check the middle element, and if they match, we found the element. But if they do not match, if the element is smaller, we continue with the left subarray. So we recursively process the, for example, this one is the sorted array. We compare with the middle element. If the middle element is equal, we are done. Recursion stops. But if middle element is smaller, we continue with the right subsection, right subarray recursively. If the middle element is larger, we continue with the right subarray. So we produce one subproblem each time at each recursive call, right? Either the right subarray or left subarray should be processed. This is the algorithm for this methodology. Each recursive algorithm has to have some base case. In this case, base case is when the array is empty. If the array is empty, we know that the recursion stops, and we know that the element is not in the array, so we return -1. So this kind of case which stops the recursion should be available at each recursive method. For example, here, having one figure stops the recursion. There is no recursive call here, right? Otherwise, the recursion is infinite and doesn't end, goes on and on. So the algorithm, and in turn the program that you are gonna build will be wrong probably. This is one of the base case. Here we have two base cases. If the middle element is equal to target, then again we stop recursion. We stop recursion when we make sure that the element is not in the array, and when we found the element in the array actually. Here we found the array, so we return the subscript of the middle element, which is the place for the searched item, right? These two cases are base cases that stops recursion, and we have the other part, the other cases In these two cases, we perform recursive searches. If target is less than middle element, we perform search on the left subarray preceding the middle element, and that recursive call will return some value, either -1 or subscript of some middle elements, subscript of the element found in the array, right? And that result is the place of the target in this array, right? So we return that value returned by recursive search. Similarly, if the target is larger than the middle element, we recursively search the right subarray, the elements following the middle element, actually, and that recursive call will return a result, and that result will be returned by this recursive algorithm. That is the correct result of the search operation for the right subarray, and since the middle element is smaller, result of the right subarray is same as the result of the whole array, so we return that value. So this is the recursion. In recursion, as I said, we should have a base case. Base case happens when the problem is very small. Either the solution is trivial or it can be solved very easily. We can stop recursion at that time and solve the problem directly. Okay, so here when array is empty, the size of array is 0, so there is no element, is the recursion. That case when the problem is very small and simple, and if there is one figure, the problem is simple and can be solved directly. If the base case is not the case, then the problem is large, cannot be solved directly. So we have to reduce the problem into one or more smaller subproblems. These subproblems are instances of the same problem. For example, here we are searching for this array, and after comparing with the middle element, we start searching on the right subarray in some cases, right? This problem is smaller. Searching the whole array or right subarray are the same problem. Again, we have a array and target value to search on that array for both cases. So they are instances of the same problem. So these smaller versions has to be instance of the same problem. If that is the case, we can solve them recursively, since they are the same problem, and the algorithm we write, for example, this algorithm can solve the problem for this large array or any subarray, since they are the same problem and this algorithm solves that problem. We can use for both problems. So we reduce the problem into smaller versions of the same problem and recursively solve them. Of course, the solution of the recursive cases will return some value. For example, here it returns a result for the solution of the right subarray, and that is exactly the result we are looking for. Sometimes it is not. We have to process the solutions, and produce the solution of the problem. Okay, so for after recursive calls, we may have some processing as well. So in algorithm design, we have to identify the base case, and we have to solve them directly. And we have to have a strategy to reduce the problem into smaller versions of itself. And these smaller problems has to progress towards the base case. For example, here we have a larger problem, make it smaller, make it smaller, 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 and at the end, we will get an empty array, right? Or we get the middle element matched with the target. So the recursion will stop eventually. We have to make sure that the recursion will progress towards the base case and stop eventually. So we have to have a strategy to reduce the problem into smaller versions. Of course, we have to solve them recursively, and we combine the solutions of the smaller problems to solve the larger problem. Okay. So this is another recursive algorithm to find the length of a string. The input is to this algorithm is a string, and we would like to find the number of characters in that string. The base case would be having one element in the string or no elements. Since we may input an empty string to such algorithm, we have to have empty string as a base case. If the string is empty, the solution is simple, length is 0. This is our base case. So again, we identified our base case. Using a string with one element as a base case will not be correct, since the input to this algorithm would be empty string, and in that case, empty string will not stop the recursion, and recursion will go on and on. It will never end. It will never reach to a string with one element. If you start with empty string, you cannot reach to a string with one element. Of course, if the string has many characters, then you are gonna reach to a one element string eventually, but it is not the case if the string is empty, and having empty string is a legal input to this algorithm, so it should be handled by the algorithm. So having one element string as a base case is not sufficient for this algorithm. Having empty string as a special case should be handled so the empty string is the base case for this algorithm, the correct base case. Okay, if the base case is not satisfied, is not the case, then we perform this operation. Here we have a string. After the first letter, we have a string as well here. So we process this string by using the same algorithm recursively. So this is the smaller version. We have just one sub-problem, one smaller problem. And we know that the first character means one character. If the length is 25, we know that the overall length of this array is 26, right? One more that because of this character. So the recursor call will return 25, and we add one more to that value and return. So the length that we should return is 1 plus the length of the string that excludes the first character, the rest after the first character, right? So we have to make sure that this recursion will stop. Actually, if we exclude the first character, the length gets smaller. We exclude the first character, gets smaller, 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 and eventually the string should be empty, right? So it will proceed to the base case, right? Eventually. So the recursion stops. We have to make sure of it. The Java code for the same recursive algorithm. So we have a parameter string, and it will return the length of the string. So usually in recursive algorithms, we have a return value, and recursive calls will return some value that is going to be used to calculate the correct result of the original problem. So in this case, this length method will return an integer value. It has a string parameter, and the base case is when the string is empty. In Java, the string is empty. Either string doesn't have any character, or string is a null string, means the reference is null. Then the string is empty. So we should control both of them. In either case, the string is empty and we should return 0. Otherwise, we should call the length method with the substring after the first character, starting with index 1, right? So this is a subproblem to find the length, and length method will calculate the length of the substring and the value of this expression will be length of the substring after recursive call, and we add one more and return as a result. Right? Simple. Probably you all implemented this several times, so I'm not going to go into detail. This is another method. Again, it prints characters in the string. As you see, if the string is null, it just returns without printing anything. Otherwise, it prints the first character and performs a recursive call for the rest of the string. As you see here, print characters doesn't return anything, doesn't need to return anything actually, since it prints characters on the screen and it completes its job, doesn't return anything. So this method doesn't calculate anything, it just prints the characters in the on the screen, so it doesn't return anything. But as you see, after this execution, the argument string is displayed one character per line, since we use print line for each character. This is very similar. As you see here, the printing is performed before recursive call, but here printing is performed after the recursive call. If you perform print operation after the recursive call, the result is printing the characters in reverse order, right? So you should be careful about it. So the operations before the recursive call are performed in the same order of recursive calls, but the operations after the recursive call, there is nothing here, but here we have some operation, and the operations after the recursive call are performed in the reverse order. Okay, these are simple examples for the recursion. Now we are going to talk about how to prove that a recursive method is performing what is intended for. So performs its function correctly. And proving a recursive method is correct and induction has very common features. Induction and recursion are very similar. As you see here, we have a base case and a general case. And recursion, remember, we prove for small values first. For example, we prove that the theorem is true for a small value, for example, for n equals 0 or n equals 1. This is the base case for induction. And if it is true, we continue with the general case, and we assume that theorem is true for all n from, let's say, 0 to n, for all the values of n. And by using this assumption, we try to prove that it is true for n plus 1 as well. Right? If we could prove that, we can make sure that the theorem is true for all the integers. Actually, we prove for the base case, let's say n equals 0. And if it is true for n, we prove for n plus 1. And it is enough for us to understand that the theorem is true for all the cases. We do similar approach for proving recursive methods. We have to make sure that the solution is correct for the base case. We have to verify the base case is solved correctly. And we have to verify that any recursive call will progress towards the base case. The recursion ends. And lastly, we have to check whether the original problem is solved correctly if all smaller problems are solved correctly. So we assume that smaller problems are solved correctly, like we assume that it is true for n. Then we prove that by using that solution, the original problem can be solved correctly as well. So like by this assumption, proving that the theorem is true for n plus 1, right? In this example, for example, we have to make sure that if the string is empty, this result is correct. We return 0 in that case, and this result is correct, right? If the string is empty, the length of the string is 0, so we verified this base case. This is not that simple for large algorithms, but this is a simple algorithm, so it is very easy to see that the base case is correct. Then we have to make sure that this sub-problems, smaller problems will proceed and will end up with base case after some time, after several recursive calls probably, right? And that is correct, since if we start with n elements in the string, the sub-problem will have n minus 1 elements, n minus 2 elements, etc. It will be 0 elements after some time. So we end up with the base case. So that's also verified. The second case is, the first is the base case. The second one is the recursion will terminate. We verified that. The last one is to verify that this, the solution of the smaller problems, if we solve this problem correctly, if the length of the elements after the first element, if the length of this substring is correctly found, if it is k, for example, the length is k, the length of this whole array is what? Of course, k plus 1. And we can verify it, right? The length for the whole array is 1 more than the length of the subarray. And if we calculate this, the length of the subarray correctly, then we can make sure that the length of the whole array is calculated by this algorithm correctly. And that makes our algorithm correct, since it is correct for the small problems, and larger problems will end to small problem base case at the end. And if this smaller problem is solved correctly, the larger problem is solved correctly by this algorithm. And this is similar to induction, and that is enough for proving the algorithm is correct. Similarly for this one, if the string is null, we print nothing and it is correct. If string is not null, we proceed with the substring after the first element. This is the first element after this, the first element, everything after the first element. And it will be smaller and smaller, and it will be empty string after some time. And the last thing here is we print the first element, right? And print the rest afterwards, whatever it is, however it prints. If this is correct, they print it. This is printed here correctly. Putting this one here will be sufficient for printing the whole array on the screen, right? So if we print the first character and the rest, we can solve the problem of printing string of characters. Similarly here, we would like to print the characters in a string in reverse order. If the string is null, we return, that's correct, and we make sure that the smaller problems will end up with the base case. These are same with the previous example. Here, we have an array. First, we print whatever here in reverse order. So we print that values in reverse order, means this one here, this one here, this one here, and this one here, right? This works fine. Correctly prints these in correct order. Then, if that's the case, then we print this one over here, right? This is reverse order of this part, and this is at the end. So the whole array is printed here in reverse order. We can see that easily. And if that is the correct, that subproblem solution is correct, the overall problem is solved correctly and it is verified, so the algorithm is correct. Okay, is it fine? Understood. So induction and proving a recursive method is very similar. You don't need to consider all recursive calls to make sure that the algorithm is correct. Of course, you can go through the trace of this algorithm. This is the trace of the algorithm. For example, for A's, calling with A's, first we call with for CE, then E, then empty string, and it will return 0. 1 plus 0 will be 1, and it will return 1. For E, we add one more and return 2, and 2 is the value for CE. 1 plus that will return 3, etc. This is trace of the recursive calls. We can trace it, of course, but it is not always easy to trace and make sure that it is correct. But This verification is a lot simpler. Here we do not consider all recursive calls, right? We just make sure that the recursive call progress towards the base case. That is usually simple to see. And we try to verify that if the smaller problems are solved correctly, we assume that smaller problems are solved correctly, and we try to prove that the original problem is solved correctly, as in induction. This is simpler to prove. If you try to trace the recursive methods, usually it's not easy. But of course, when you run this method length for A's, of course, there will be several recursive calls, right? Made. These are the recursive calls made by the Java virtual machine. Java virtual machine should handle it, and it handles it by a stack of activation frames, as you all know. This is called runtime stack. So for each recursive call, we add another activation frame in runtime stack. And activation frame, as you all know, contains method arguments, local variables, and return address. Right? This has been covered several times before, so I'm not gonna go into more detail. But whenever a method is called, a new activation frame is pushed into runtime stack, and when we return from recursive call, that activation frame will be removed part from the activation frame, and we know the return address from that activation frame. So this is the runtime stack. First, we pushed a recursive call for A's, then CE, then E, then null string, empty string, and the run of the code for empty string will terminate right away, since the string is empty and we know that the length is 0. We just return, and we return to the code for this recursive call, and where we left in that recursive call the calculation of recursive call. And after we return, this activation record will be deleted, and the new stack will be like this, etc. So we put the activation records and remove it. We put them with the recursive calls and remove them while the recursive calls terminate. There is an analogy for the runtime stack. It is simple. Just I will go over it. Assume that there is a tower, office tower, long building, tall building, where at each level there is an employee, and there with some list of instructions. At the bottom level, this is the recursion. At the bottom level, the employee carries out its part of instructions and call the employee in the next level and put on hold. That's important. It puts on hold for the employee at the next level will finish its job and return its call, right? And that the employee in the next level will start working on its counterpart. When it completes its part, it calls the employee at the next level and put on a hold. And the employee at the next level completes the part of instructions and calls the employee in the next level and put on a hold, etc., etc., until at the top level, there is no next level. So the employee performs its job on the instructions he's given. When the employee at the top level finishes instructions, returns the answer to the level below. The employee at the level below resumes its operation and finishes the job and returns the result to the employee below, and the employee below resumes when finished, returns the answer to employee below. It continues until the bottom level is reached, and at the bottom level, when the instructions at the bottom level completed, all instructions are executed and the result is available. So it is like it goes one level up, one level up. Uh, it is shown in reverse order, but one level up, one level up, one level up, and when the top level is handled, one level down, one level down, one level down, and return right at the bottom level. So this is the trace of the algorithm. As I said, you do not need to trace the algorithm to verify that algorithm performs its job correctly. It is not always easy to trace all the recursive calls, but it's better to prove the recursive method by using this three-step verification. Is it clear? So it's almost time to stop. I will stop here and we will have 10 minutes break. After the break, we are going to continue with analysis.